x squared. If I was to take and find the domain, I'm going to have to flatten that thing down. Okay, I flatten it, and everything gets pulled down. Okay, for my domain, okay, making that go forever. So it is all reals. But my range, okay, flatten that thing to the y-axis. It's going to be all positive values. So all of our values that are bigger than and could be equal to 0. A cubic function. A cubic function that's going to look like this. Okay, so our cubic function domain. Okay, I'm going to flatten that thing. Okay, when I flatten that thing, it ends up flattening out that way. That means all of these points, even though they will go that way forever, they will go that way forever. You know, like you can show it right up there. And so we have all real numbers. My range, same thing. Flatten it this way. Pull all those values in. Pull all these values in. It is all real numbers. Next one here is a square root function. Okay, that's going to be the inverse, okay, of this that way, but this is not a function. When you look at the inverse of a quadratic, okay, so we have to deal with the positive square root, or you have to deal with the negative square roots. Okay, so when we do a square roots okay, function, and it's a positive square root function, this is the square root function that the end behavior ends up being positive. And so our domain for this one, okay, you're going to flatten that out. Okay, everything's pulled down okay, to the x-axis to give us all numbers that are bigger than 0. And this thing does get forever big, way down here. So when you flatten it this way, that means everything's going to be pulled to the y-axis. So y values are also bigger than 0. Cube root, cubic, is going to be like this. So if I reflect a cubic over y equals x, okay, it ends up going like this. Okay, so we have our cube root, okay, function right here. Okay, flatten that down to the x-axis. So everything's moved to the x-axis. And my domain is all real numbers. Flatten it to the y-axis. All of these values continue to be pulled right down to the y-axis. Are all real numbers. Questions so far on those graphs? Alright, reciprocal functions. It has two branches. We have this one right here where it's going to get close to. Does anybody remember what these things are that they get really close to but they never touch? asymptotes. Asymptotes. Yep. Okay. So on this one right here, if I was to flatten this thing out and pull everything down to the x-axis, then it's going to bring all of these things down. Okay, but there's not going to be anything there at 0. Because there's nothing that's going to touch this asymptote at 0, but it's going to go forever that way. It's going to go forever the other way. So this is domain's going to be everything, okay, but 0. Okay, there we go. Set notation is the fastest way to do that one. I haven't done set notation yet. I usually do interval. We did do it in interval notation. We're just going to have to put it goes from negative infinity up to 0, not inclusive. Goes from 0 to positive infinity, not inclusive. So you don't have to do both, but that's how you do it. And we do the same thing. Okay, when I come up here with the y-axis, I'm going to take all of these points. Okay, and they all pull everything down. Okay, so you end up getting a hole, again at 0. Okay, because there is a horizontal asymptote on this as well. Okay, at the x-axis. Okay, so we do the same thing here. Y such that y is 0. Exponential functions end up having a asymptote as well, right here, a horizontal asymptote. Okay, that'll reach, okay, but never touch. Okay, when we talked about exponential growth and decay, when we talked about decaying, this is a growth function. Okay, but when we had an exponential growth or decay function, so it's getting really, really decaying, really, really close to 0. Okay, so as a virus or something decays, it decreases exponentially. Okay, it'll get close to 0, but there'll always be, some traces of it around. That's where we talked about those. Okay, so we have exponentials. It didn't matter what was here. We could add it to the x power. Okay, it's just going to be a different steepness. E, does anybody remember what the value of E was? I did 2 to the x. 2 point something, yeah. 2.71. There we go, 2.71. Okay, so our domain, okay, on this one, we're going to flatten this thing out, and even though it does keep on going, it will, keep on going forever in that direction. Okay, so everything that's going to be pulled down is going to be pulled down forever, so it is all real numbers here. Okay. No, this one doesn't have a vertical asymptote, so 0 is right here, and it does get pulled down right there. Okay, so everything on this one, okay, is being pulled down, and this is going forever that way. Doesn't matter if it's growth or decay. Right there, so I'm going to mess up here. So if you're looking at this one right here, I'd pull all these points down. Okay, here, 0 gets pulled down, these get pulled down, it goes forever that way, and it's going to go forever. Okay. And the range, everything's going to get pulled to the y-axis. Okay, it'll be going forever high, so it's going to get forever large. But then we have the asymptote, okay, it gets pulled down to. It cannot equal 0 because it's not going to touch that asymptote, but it will get everything larger than that. So we have a y, okay, that does not include 0, but does get into the y. All right. Logarithm, natural logarithm. It doesn't matter if this is a normal log, okay, or a natural logarithm. A normal logarithm is base 10. What's a natural logarithm's base? remember what natural logarithm stood for? No, well, what? Log base e, is that what you said? Natural logarithm? Yeah. Yep. It is log base e. Okay, so it's a log base 2.71 power. Okay, so that's what a natural logarithm, okay, was right there. In other words, it didn't matter what logarithm base you have. A logarithm right here is the inverse, okay, of an exponential. So if I was, okay, reflecting this right over here over the y equals x-axis, okay, this graph right here ends up, okay, looking like this right here. It's going to come close here, and then go like that. That's the reciprocal, okay, of that function right there. And these two are reciprocals, okay, are inverses. So as I look at this graph right here, my domain, I smash it all down. I don't get 0, but I get everything else gets pulled down. So I get x such that it's bigger than 0. Yeah. Not equal to 0, not bigger than it. And the range, okay, this goes forever high. Okay, so when I pull this down to the y-axis, smash it to the y-axis, okay, it's going to go forever high and forever low. It will include 0 on this one too, because I'm pulling that part right there in. All of these points, the whole line gets in there. So it is all real numbers. Oh, you got a lot of mics on the back. Did I not give you time, or did we forget this? Oh, there's one back. Yeah, there's back. Yeah. Absolute value. You guys remember that one, don't you? It's a V. Yeah. Right, absolute value. Those are V's. Alright, so we remember those. Direct variation. The direct variation is a linear function. The only thing that a direct variation has to do is it has to start at 0. Okay, so the direct variation is going to have, okay, a y-intercept of 0. So it's a line. And we draw a line in that. A linear function. Rational algebraic expressions. You guys remember graphing some of those? Those were from last year. We had the vertical asymptotes and the horizontal asymptotes, and then you had different divisions of them. They look very close to your reciprocal functions. Now those are the harder ones, I think, to remember. Okay, so 11, A and B are they're the harder ones to remember. Here's my direct variation, okay, which is all real numbers for both of these. Okay, all reals. Okay, absolute value. I just did that quick because we already did a linear function. We'll go back there if you want to be sure there. Absolute value here, we had a V. Okay, so this one right here, if I do a linear or array over here, okay, that's going to pull down, so it goes forever to the right. Pull these all down, smashing it down to the x-axis. Pull it to the left, and my domain then is x, all real numbers. Whereas I'm going to pull these in. That means it starts here and goes forever high. Oops. An equal 0. I need the back bracket here. Okay, so it equals 0. Infinity can never be reached, so that's why it's always a parenthesis. This one's an easy algebraic expression right here, because these things cross off. Whenever you cross something off, what does that create in the graph? constraint that we called a hole in the graph. You guys remember graphing those things that you had holes in? No? Okay, remember that one thing I told you, the hardest thing about this class is going to be remember the algebra 2? Okay. It will. Okay. This part right here, I have y equals 6. Okay, that shouldn't be at 1 right here, but this should be at 6, which is going to be, I want to put here. Okay, where my y is 6. Okay, but there's going to be a hole. Okay, a hole somewhere on this graph. Okay, and the hole is going to be where this x plus 1 equals 0. So x cannot equal negative 1. So I come over here where x is negative 1, and I go up to the graph and put a little hole right there. Okay. Now this domain and range for this algebraic rational expression, okay, is going to be domain. I smash this down, okay, and I get this hole right here is going to come down, big hole there, and all of these other lines or points end up going forever to the right. All these other ones go forever to the right. Alright, so my domain, x, such that it cannot equal negative 1. You can put that in if you wanted to put it into set. Okay, if I did it in interval, it goes from negative infinity up to negative 1, non-inclusive, and then from negative 1 to positive infinity, and non-inclusive on both ways. My range, okay, smash this thing into the y-axis. That means this point right here, that means this point right here, that means that point right there, that means all these points right here are all going to be smashed in. So this open circle gets right there on the y-axis. But then this solid circle right here, as I move that in, ends up covering it up. So I get one little dot. That's 6. That's how you say it in interval. Set notation's a lot easier. Such that y equals 6. Right, you'll see it there written in set more than, or sorry, interval more than set. And our last one right here was, okay, if it wasn't a rational algebraic that had a top and the bottom canceled each other out, it left something in the denominator. Okay, it ended up doing just like the reciprocal function. Okay, the only thing different about the reciprocal function is this right here was, okay, stretched a little bit more. Okay, and we had, okay, a vertical asymptote that went one to the left. Okay, if you cross something off, that created a hole. But if there was something left in the denominator, we always set that equal to 0 again. So we had a vertical asymptote at negative 1, and that's where this is right here. And then we had a horizontal asymptote right at 0. And then our graph went like so. Well, looking here at the domain. Okay, this right here will crunch down here so we get everything that goes this way. This right here will crunch down so we get everything that goes that way. So is it all real numbers then? What would you say? Is that all real numbers then for the domain? Everything but the asymptote at negative 1. Okay? Because nothing can touch this negative 1. That's what an asymptote is. Okay, we had an asymptote right here at the bottom at negative 1. So that's what that value means. Okay, so our domain is x, maybe I'll put it in sets because I'm running out of room. X cannot equal negative 1. And if I put this thing into interval notation, or sorry, if I do the range, I smash it in this way. So everything's going to go in this way, So we could go forever down that way, because that's what happens here. That goes forever that way. This could go forever high that way. Nathan, all real numbers in this one? Yeah? Some of you are shaking your head. Except for the 0. There was a line, there was an asymptote right here. So when I smash that in, there's a right there at 0. Okay, nothing's going to be there, so this one right here is everything, okay, but 0. If you wanted to say that again in set, you'd have to say it goes from negative infinity all the way up to 0, don't include it, and then go from 0 to positive infinity, and then we go. Alright, so, okay, I'm going to actually teach you guys how to dance. You guys look like you're wiped out or exhausted. So we're all going to get up and we're going to do some dances. Okay? So when you guys get out to homecoming, you can get out there, I'll be out there supervising that dance and having to walk through the mob of everybody. And so then you can get out there and do the function dances instead. All right, come on, get up. Get up. Come on. Come on, you can do it. These are better dances because they're some of the ones you do. You're going to volunteer to be up here in front?
No.
No? Okay. Nicholas is not going to lead us? Alright. So, the graph. F of x equals x. It's going to be a line. Okay, there we go. That's a good move. There we go. Okay. Then x squared. What's that dance look like? There's pretty fun dances so far. You got it. Okay, x cubed. Like this. Yeah, it's a little S that goes down. Yeah. Square root. Yeah, teapot. There we go. Teapot. There we go. Pretty good one. Logarithm. There we go. You got it. Going that way. Cube root. It's the inverse of it. Okay, so it's going to be going this way. Okay, that way. Oh. How about, well, I said that was exponential, sorry. Now the logarithm. Okay, the logarithm one is going to be going the inverse of the exponential. Okay, so the exponential, okay, grew, okay, like, whoops, I'm going backwards for you guys. This way. Okay, so then you're going to reflect that, okay, over, okay, the y-axis. Okay, so there we go. Going down like this. Absolute value of x. Oh, there we go. Do we just need some music to this and everything? Is that what we need? No worry, we'll add some music. What happens if I put a 3 out in front of it? What does that do to the absolute value? What's it do to a slope if you put a 3 out in front of a line?
Makes it narrow.
Okay, makes it more narrow. So there you go. Your v goes like that. There you go. Okay. Well, how about if I did the absolute value and I put a 3 out behind it? This is when our moves start getting better. Yeah, there we go. Oh, there we go. We got 3 hops. Okay. No. All right. Sit down. You guys, I'm going to have to get the music going here to make sure that I really get some good dances. We're going to get some better dances once we learn a little bit more about our moves, because this is kind of boring, moves so far. We got to learn to move to the left and then down and then flat and flip. We'll get some good ones. All right. Here you go. Basic functions. Okay. If we have anything in our basic functions right here, okay, we have f of x equals, okay, a. A is considered our vertical stretch or compression. Okay, whenever I put this number out in front, this 3, okay, that went out in front. Alpha function that vertically takes a function and is going to stretch that function. The b value, okay, affects this x component. The x values are always horizontal movements. That's what's on a graph. The x is horizontal movements. So the x is going to be a horizontal stretch or compression. Okay, that's the b value. The b is right next to the x. Okay, it's inside these parentheses. Okay, right next to that x. That's how I remember that the a always is vertical. Okay, because it's outside the function. Okay, and b is inside next to the x's. Okay, so if I was to put inside this right here, a 4x right there, that 4x is going to be horizontally affecting it. You know, horizontal, sometime I'm going to be stretching it or compressing it. And we'll talk about what it's doing here in just a second. Okay, the h value is the horizontal translation. Okay, so that's going to be this movement. Okay, or this movement going that way. Okay, so we have a horizontal translation. So when I put something inside the absolute value right there, so if I put plus 3 inside that, okay, that's going to make us go 3 to the left. Okay, 3 to the left. Okay, and the k value, okay, the number on the outside, that is going to be the vertical. And the vertical translation. So if we're looking at these parent functions right up here, if I have the parent function, the absolute value of x, okay, if I have our new transform function, the absolute value of x plus 3, h is the vertical translation. This function right here started here and it went up, okay, 3 units. Okay, if I put a -7 outside of the absolute value, same thing right here, it's absolute value, but instead of going up 3, okay, this thing's going down 7 units. If I want this thing to go left or right, okay, you have to take that translation function and put it in with the horizontal movements. The horizontal movements go with the x function. The only thing you got to be aware of, and I cannot say this enough, be careful with what's in the x. The vertical movements, they're very easy to see. The horizontal movements, they're not so easy to recognize. You look at this right here and you're going to say, does this go left 7 or does this go right 7? Yeah, 50-50 guess right now. Tell your neighbor next to you. What do you think? Right 7 or left 7? Only thing I can do to save your butt is tell you this. I will say it like a broken record. Whatever's in the horizontal component, set it equal to 0. Okay, it will define itself once you solve it. So if I'm going to move this thing, okay, you can see this one right here. I had it graphed, so it's pretty obvious. Okay, it moved right 7 because I took what's in the absolute value and I set it equal to 0. The reason I tell you that is all of a sudden I'm going to put a 3 in there. It's going to be 3x minus 7. Does this still go left? Or sorry, does this still go right 7? You don't get in the habit of just looking at that and say, oh, I'm just going to do the opposite of what it says there. Set this equal to 0. This doesn't go right 7 anymore. This only goes right, okay, 2 1/3. Only shifts right 2 1/3. Set what's in the absolute value equal to 0. That will tell you, okay, its translation factor. There's x plus 8 right there. Okay, that one right there, I'm going to set this equal to 0. To see that, we're going to move this thing left, and move from here, left 8 units. Okay, whenever we want to reflect something, we can either reflect it over the x-axis, or we can reflect it, okay, over the y-axis. Okay, if we want to reflect something, okay, over the x-axis, this is going to be, okay, something that's moving vertically up or down. Okay, we are going to take and put the negative on the outside, because if you think about this, absolute value, doesn't absolute value mean to take the number you have, like the absolute value of 5, is what? What's the absolute value of negative 5? So know what? When you do absolute values, don't you always get positive answers? So what's the opposite of always getting a positive answer? This is that way. Going down is opposite of always getting positive, negative. You reflected this thing, okay? It's a reflection over the x-axis. Let's see me. Okay, abbreviate that. ROX, rocks. Okay, you're going to rocks. Then we're going to Roy. Okay, this way. Okay. Alright, so our reflection's right up here. Okay, when we're talking about a reflection over, okay, the x-axis, and I have something up here typed in wrong. Here, when I reflected over the y-axis, this is going to be moving in the x direction. That's taking my x's and negating them. So if I want to take my x's and move them, that's this direction right here. That's a reflection over the y-axis. Okay, this one right here, if I wanted to go across the x-axis, I negate the entire function. If I wanted to go across the y-axis, I negate just the x's. Okay, an example of a point right up here, if I was to take and reflect this point across the y-axis, or sorry, the x-axis. So if I have 4, negative 8, okay, so if I go over 4, down 8, okay, right there, and I was reflected across the x-axis, which one of these functions, okay, would be, if I reflect that across the x-axis, tell your neighbor which one of these functions, okay, taking that right there, if I reflect it across the x-axis, which one is it going to be? Okay? Which one of these functions is a reflection over the x-axis? The negative on front or the negative on the inside? Okay? Reflection across the x-axis. That one right there. So this is a reflection across the x-axis. This right here is a reflection. The red one, I put it in red, is a reflection across the y-axis. I negated just the x component itself. Alright, graph paper. Didn't I give you some graph paper yesterday? Yeah? Isn't it blue? In blue? Then go ahead and get that out. Using graph paper. Alright, stretches and compresses. Okay, go ahead and graph on your graph. Y equals x squared. Y equals x squared. I have the y equals x squared, and I was to now graph y equals 2x squared. You can see right up here, and I guess I have the t-chart for 3x squared. But what I'm doing for all of these right here is, okay, as I do that, okay, I'm tripling all the y coordinates. So I'm squaring my values still, just like I squared right there. But then I'm going to find my y values, the x values are staying the same, but my y values every time are tripling the amount. This amount tripled. This amount, I can't triple 0. That amount tripled. That amount tripled. You can see right here, as I graph that, y equals 3x squared. What happens to the function? Does it get wider or does it get skinnier when I triple it? So what's this called? Is this a stretch or is this a compression? This right here is vertically happening to something because we put it on the outside of that function. So it is vertical. And to make my parabola get skinnier, okay, John, can you put your hands up here so you can do that? There you go. If I was to make his hands skinnier vertically, I would have to pull him this way, right? But I could have a horizontal reaction to this too. How could I make your hands skinnier and do something horizontally to you to get a skinny parabola? Would I have to pull his hands out, or would I have to push his hands in to get it to be skinny? If I pull them out, does that make it skinny anymore? That's called a horizontal stretch. I mean pulling out. That's stretching him this way. If I want to get it skinny, okay, I end up having a horizontal compression. A horizontal compression ends up being the reciprocal factor, okay, of something. This right here, okay, that's a nice wide one. That's a vertical, okay, that's a vertical compression. Put your hands up there again, John. Oh, you take it all. Vertically, take his hands, push down. I'm compressing it vertically. Made it nice and wide. Vertically, stretch it, nice and skinny. Okay, these are all vertical, okay, movements to one another. Okay, you're going to sketch a graph, okay, and describe the transformation that occurred to that function right there. Again, something you've all done in Algebra 2 many, many times already. Vertex is the most important part to find first. There's nothing afterwards. So when we look at this in vertex form, where our vertex is our h and our k factors, we set what's in the inside equal to 0. And that helps us find the x component for the vertex. So this thing right here has been shifted, right, 3 units to the right. It's going to have a nice line of symmetry. Okay, right there at x equals 3. Is this graph going to go up or is this graph going to go down? Has it been reflected of any sorts? It has not. So this graph is going to go up. Now I put this little dotted line here because I'm not going to judge your artistic talent. Some of you made this next one wide or skinny, and as I looked around, I could not tell. Okay, in other words, if this is the parent right here, and I was to take that parent away, and I put this on here, what do you think? Is that wide or skinny? Hear me now. You sure? You're not really? Okay. Let's put the parent, put the parent back on there. Is it wide or skinny? Skinnier than normal, right? So if you put the parent on there, I don't have to judge your artistic work. Okay, otherwise, I don't have a clue. Okay, if otherwise you're gonna have to come up here and do a T-chart every time and plot those points and get them up there so I can tell whether it's wide or skinny. This little parent function allows me to determine, oh yeah, they meant to make this thing skinny. The parent may be a little wider than it should be, okay, but they're drawing it inside the parent, so that's a horizontal stretch, or sorry, a vertical stretch. Okay, and that's what it said right down here. Describe your transformations. Okay, this is a translation. Right, 3, and a vertical stretch 2. Two transformations that occurred on them. So this dance move, when we actually do this, some music tomorrow, and actually make you guys look good, okay, it's going to go, okay, this way. 3 and like that. And I know you guys can't wait. It'll be the first day everybody skips. Alright. So we have f of x. Oh! That's not the end of the day. We gotta go back. Alright, we got f of x equals 1/5 times x minus 3, the quantity squared. Go ahead and graph that one. And describe the transformation that's occurring. Don't worry, I got a couple days to make it look good before we get out of the dance floor and do that on Saturday. Nothing really changed on the translation. Still have a line of symmetry. F3. Is this parent function going to be one that's going up, or is this parent function going to be one that's going to be going down? So if it goes down, I want the parent to go down with it so I can tell if it's wide or skinny. This one does go up. Okay, so that's about, whoops, that's not very symmetrical. Okay, there we go. That's a really good dotted line. Okay, but then we have 1/5. Okay, 1/5. Okay, and it's vertically. Okay, and I always, it's not a good idea to teach you this, but if you always forget, and you say, oh crap, is that going to be wide or skinny? I always forget. If I rise 1, run 5, does that end up giving me something that's going to be wider or skinnier? You cannot really do that because it's not linear. Okay, but that does give you something that's wide. I really don't care how wide it is. Try to make it symmetrical and show that it's wide. Okay. All right, day 1 of dancing is over with. Okay. Can't wait for day 2. End of day 1.